Test, test. Okay. Okay. Hello, everybody. Hi. Good afternoon, ladies and gentlemen. Okay, welcome to the first of the many "Why Should I Care About" seminar. Okay, I'm the host for today, Kai Shin from Physics Year 1. Hello. Hello. Yes. Okay. So how many of you here actually knows what you are going to expect in the near future when you are out there working in the industry? I suppose a lot of you all don't really know, right? You are still a bit lost about how industry is like and why you are here studying math and solving equations. And so that is why we organized this seminar today and ask professionals from the industry and even our academians to share with us, share with you guys and me definitely about why is math important, especially in the industry itself. Okay, math is not just equations that you solve in your tutorials. Math is actually something that is very interesting that will help you in your future. Okay, so last year there's this particular student who are equally lost like you and me. Okay, so excuse me. So yeah, so they decided to find out that if what he's learning is actually useful in the industry itself. So decided to organize this seminar and get everyone together and know what to expect in the future in the industry itself. So this person is none other than Ling Ching An. Is he here today? Yes, a very wonderful person there. Okay, he organized this thing to know more about himself and me and definitely the people in the industries. So so ladies and gentlemen, today is the first of the many to come. We are going to talk about lines, straight lines, and many straight lines putting together. Okay, that's actually layman's term. I think all of y'all should know that what is linear equations, correct? Am I right? Yes, so I suppose all of you all know what's a linear equations. So what could be more boring than having straight lines everywhere? Yes. So, and worse, many different straight lines coming together, them forming into things like parallelogram in many different dimensions. So do the industry really need straight lines and parallelograms, you might ask? And yes, I'm here, no, not me, but yes, the speaker is here to convince you that actually they do need straight lines and parallelograms, in other words, the linear equations. So linear equations is required in many industries, from the image compression to aircraft design to finance and biology, on to even to chemistry. All this requires the basic fundamentals of solving linear equations in one way or another. So in other words, yes, linear equation is definitely important in the industry itself. So today we'll show you the link between linear equations and science. Yeah, something that we all know. And now let's put our hand together and welcome our speaker for today, Professor Hirao, and to share with us why I care about linear equations.
So thank you very much, Kai, for a very kind introduction. And I think this is a very good idea to do this kind of seminar. And I was informed that today's audience is the first year students, but I'm happy to see many other students who don't look like year one students. Anyway, welcome to this seminar and thank you for coming. So today I'm excited to tell you about this assigned topic, which is why I care about linear equations. And as Kai said, I'm from SPMS, but I'm from CBC. I'm in CBC, I'm studying chemistry or biochemistry. Right? And then why should I care about linear equations? That sounds strange, right? But if I look around and see what I'm doing carefully, I realize that we are certainly using a lot of concepts of mathematics, even in the research of chemistry. So this is particularly true of myself because my research area is computational chemistry. So here, computational literally means that we are computing something, which sounds like we are using some sort of mathematics. So I want to explain how we are using mathematics. But before that, I have to confess something to you. To be honest, I rarely care about mathematics as a matter of fact. I rather care about the chemistry. This is my real interest. People say that chemists are not so good at mathematics, but this might be a misleading statement because I know many chemists who are good at mathematics, but at least I'm not so good at math, and you are certainly better than I am. And anyway, to be honest, I cannot solve any difficult equations. So what I do is actually let computers do everything. So I'm not solving any difficult equations manually. But here I want to make an excuse because the main reason I use computers is not because I'm not good at math. The real reason is that the equations we want to solve contain many variables or operations, so that even for mathematicians, solving equations requires the use of computers. So it is essential for anyone to use computers when applying chemistry to, when applying mathematics to chemistry problems. Okay? So now coming back to the reason why I care about the linear equations. Too rush. Okay. Okay, so now let's come back to the reason why I care about linear equations. The reason is simple. This is because linear equations are useful in solving many problems in chemistry. And in practice, we actually use matrices because matrices represent linear transformations, such as the ones used in computer graphics. And for me, the main reason I use matrices is because matrices are useful in solving so-called quantum chemistry equations. This is, for me, most important reason I use matrices. And so let's recall now what matrix means. But today, I'm not going into too much detail because you have just started learning here at NTU. And I heard that you will learn most of the important concepts later this semester or in the next semester. Right? So I just review only important fundamental concepts. And if you don't understand, or if, in case you cannot follow something on the slides, no need to worry, because in any case, you will learn everything some other day in lecture hours. So now the matrix is an array of numbers that somehow looks like this. Okay, so you see the matrix is composed of many rows and columns, and each element, each number is called a matrix element. So this looks like lecture theater, and the numbers of rows and columns can be different. That means that in general, the matrix can be rectangular, right? And this is an example of a rectangular matrix. In this case, this is a 2 by 3 matrix. And here you can see there are 6 elements in this matrix. And in this second example, the numbers of rows and columns are both 2. In such cases, we specifically call it a square matrix. Okay, so now from now on, for simplicity, let's focus on this kind of square matrices. So the matrices can have any size depending on the numbers of rows or columns. In this square matrix, this n value can be as small as 2 or even larger than 1,000. So the size of matrix really depends on the problem you want to solve. Okay? So using these matrices, we can do a variety of operations. The simplest one is matrix addition. Here we we do the addition of two matrices of the same size and then get another matrix, C. And to get C, we just take the sum of the corresponding elements. For example, here, the 1, 1 element in C is just the sum of the A11 and B11, right? So we just do the same for all the elements here in this matrix. So it's straightforward. This is a very simple example. Here, the 1, 1 element is 2. This is because of this one plus this one. Okay, and we can also do matrix multiplication. Here, we multiply matrix A by another matrix B to get a new matrix C. Here, the calculation is a little bit more complicated than the addition. But in this example, here comes 7 because of 1 times 1 plus 2 times 3. 1 plus 6 equals 7. Right? So it's not so difficult. And we can also do matrix vector multiplication. Here, A is a matrix, and B and C are vectors. So here you can see that if you multiply by matrix by vector, you will get another vector, C. Okay, and in this example, this is 5 because 1 plus 1, 1 times 1 plus 2 times 2, right? Okay. Okay, so as I said, matrix is an array of many numbers, or many elements. But there are several special cases. This is a summary of special matrices. This is called a diagonal matrix because although there are many elements in the matrix, all the off-diagonal elements are 0, and only diagonal elements can be non-zero. So these are called diagonal matrices. And this is a kind of diagonal matrix, but in this case, all diagonal elements are 1. And this is called identity matrix. And this identity matrix I is interesting because if you multiply some matrix A by I, the result remains to be A. So this I is similar to 1 in this multiplication of numbers because you know that multiplication 1 doesn't change the original number. It's quite similar. And how about this? This is called zero matrix because all the elements in the matrix is 0. And if you multiply A by 0 matrix, the result will be the 0 matrix. Okay? And again, this is similar to 0 in this multiplication because this will give us 0 as a result. Okay? And this is inverse matrix. Inverse matrix for A is denoted like this. And this will satisfy these conditions. Okay? Here, when you multiply the original matrix A by its inverse, then it will give us identity matrix I. And this is an example for a 2 by 2 case. And this is, again, similar to this multiplication of numbers. Okay. Okay, so in fact, there are many other interesting concepts for matrices, but it seems you will learn all these concepts later this year. So look forward to studying these concepts in lecture hours. And as I said, I'm not so good at math. After that, please come and teach me these concepts. Okay, so now let's consider how we do these operations in practice. So when we deal with 2 by 2 matrices, you can see this is quite straightforward. So you can do this even with a paper and a pencil. It doesn't take any time. You can finish this calculation within a few seconds, right? But what if we have 1,000 rows and columns? So of course, each operation is straightforward, and it is not impossible to do this, everything with a paper and pencil if you are patient. But the problem is that there are too many elements, 1 million elements. That means it will take too long time hours or days. And after the calculation, I will be totally exhausted. Maybe sometimes I have to charge the battery by having energy drinks every few hours. And even if we somehow complete all these boring calculations, most probably the result will contain a number of errors. Then if we again check the result, then it will again take time, and it is not at all efficient. Okay, so instead of doing all this by hand, I would rather resort to a computer. If we use a computer, this calculation can be completed right away, even if we have millions of elements. And of course, if we want to let a computer do some specific task, we may have to use some programming language, but you can just write a few lines of code, and then you can do addition, multiplication, or whatever you want. You can easily do this kind of operation. Okay? And so today's goal is to explain how these concepts are related to the real world. And I think the best example is rotation. So let's have a look at rotation here, especially the rotation of molecules, because I'm studying chemistry. Okay. So before that, in my research, what I want to do is that I want to understand the chemical and biological molecules. And one of my research goals is to understand proteins. You might have heard of proteins. Proteins are very important biological molecules, and they can sometimes trigger intractable diseases. Right? So first I want to understand the structure of protein. But the problem is that the protein contains thousands of atoms. But the experimentalists can determine the positions of all atoms in the protein. And after that, they give us this kind of information in which the positions of all atoms are described in the form of x, y, z coordinates. So this is x values, these are y values, and these are z values. However, you see from these numbers, a lot of numbers, we don't get any image of the protein structure. We are just looking at a bunch of numbers. We don't get any image, right? So what we do next is to visualize the protein by using some software. So after visualization, we can get a much clearer image of a protein. Right? But there is still a problem. This is not sufficient enough, not yet sufficient, because you can see there are so many atoms in the protein, and the structure is not so simple. That means I want to inspect this structure from different angles to better understand the structure of this protein. Okay? So for that, we need to rotate the whole protein. Okay? So let's now rotate the protein. This may not be a good example because this contains not only the rotation, but also some other transformations. But anyway, I think I can convince you here that if we rotate molecules, we can understand the complex structure much better. So rotation is a very important transformation in chemistry and biology. And now the question is how we can rotate the molecule mathematically. This is a question. And to simplify the problem, let's consider this very famous molecule, a water molecule. And this is a very simple but very important because 60% of our body is nothing but water. And before rotation, what we have to do is first is to determine the positions of all atoms. And for that, we need to define x, y, z axis. And this is kind of arbitrary because there are many ways of defining x, y, z axis. But let's do like this here. So we place this oxygen atom at the origin. And then we assume that this molecular plane comes just on the XY plane. And then this y-axis is going through the oxygen atom, and it is bisecting this HOH angle. So, and here I'm not showing z-axis, but because z-axis is perpendicular to the plane. I mean, the perpendicular to the slide. But you can imagine z-axis. Okay? So that way, once we define x, y, z axis, we can know the specific positions of all atoms. So here, let's see what positions look like. So in chemistry, we often use the unit of angstroms. So these values are in angstroms. So and as I said, I placed the oxygen at origin. So all these values are 0. And the second hydrogen is on this side. Therefore, the x value for this hydrogen is negative, as you can see here. So that way, we can define the x, y, z coordinates. And the next question is, how can we rotate the entire molecule around the z-axis? As I said, the z-axis is not shown, but it's perpendicular to the slide. Okay, so this is a question. And this can be done by using this rotation matrix. Okay, and what we do is let some x, y, z coordinate act on the this matrix act on some x, y, z coordinate, and this is nothing but multiplication of matrix and vector, and then we can easily get another vector C here, and this vector is not x, y, z coordinates after the rotation. So I think the important message here is that a matrix is not always just array of meaningless numbers, but it can have some specific meaning of some kind of transformation. So this is why matrices are very useful in the real world. So let's now think about how we apply this matrix to this water system. Let's rotate the water molecule by 90 degrees. So we have rotation matrix, and we also have x, y, z coordinates for water molecule. And first, we take the x, y, z for oxygen atom, 0, 0, 0. We change it to a column vector and place it on the right-hand side of this matrix. And then we can get a new x, y, z after rotation. But in the case of oxygen, all values are 0, and so these remain 0 even after rotation. But for the other two atoms, this operation will change the x, y, z coordinates, so that you can, if you compare carefully, you can see that values are slightly different. Okay, so here let's see original coordinates in red and the new coordinates in blue. Okay? So you can see that the oxygen atom didn't change because it's at the origin, but you can see the entire molecule rotated around the z-axis by 90 degrees. So this is how we rotate the molecule by using matrix. And of course, we can rotate molecules about x or y-axis as well. And these are corresponding rotation matrices. And here I wanted to say that, I'll tell you a little bit about the combination of two rotations. If you want to rotate the molecule first about x-axis and then y-axis, then the corresponding matrix will be represented as a multiplication of these two matrices. And if you want to change the order of these operations, of course, you have to change the order of this multiplication. Okay? And so after the seminar, I think you can try these multiplications, but you will see that the results will not be the same, will not equal each other. And to express this, we say that these matrices do not commute. I mean, A times B does not equal B and A. And this is quite different from the multiplication of numbers, because here the order doesn't matter. Right? But for matrices, the order actually matters. So I think you can keep it in mind. This is very important. Okay, now, so we have seen how we rotate molecules, but I actually want to study proteins. And if we study a protein, problem is there are so many a number of atoms. And I don't want to get exhausted by doing so many rotation operations. So again, I will use computers to do everything. Okay. Yes, and the second example is quantum chemistry. And actually, this is the main reason I use matrices. But today, I'm not going into too much detail, because we need some knowledge about advanced concepts to understand quantum chemistry. So let me just tell you a rough idea of quantum chemistry. Okay, so why should I use quantum chemistry? This is mainly because I want to understand chemical reactions. You know, in our CBC division, we have so many good professors, postdocs, students, and they can synthesize new compounds. I mean, they mix something and get another compound. And you know, there can be an infinity of compounds depending, which differ in how atoms are bound to each other. But sometimes the resultant compound can be very useful for our lives. For example, the compound can be a very powerful drug that can combat difficult diseases. And just as an example here, I show you a very famous drug, Tamiflu. I guess you might have taken this when you got flu. Okay? And when we usually take drugs in the form of capsule or powder, but a really important ingredient is this kind of compound. There are so many compounds inside this capsule. Okay? So this way, compounds can solve the problems we have in our real life and improve our lives. So I think the chemical reactions are very, very important. So I want to study chemical reactions, but what do I mean by that? What I mean is I want to know the mechanisms of chemical reactions. So when a reaction takes place, we know the starting material and the final product. In other words, we know the input and output of a chemical reaction. However, in many cases, it's not clear to us what's going on in between here. So we don't know why we got some specific product. So if we understand the reaction mechanism, we will understand the reason we got this product. And based on the reason, we may improve or develop better. We may be able to develop better reactions. For example, we can accelerate the reaction rate, then we can get the product much more quickly, or we may come up with much less expensive reactions, or we may devise safer alternative reactions that do not require the use of toxic or explosive reagents. Okay? So how can we study chemical reactions computationally? So these are the examples of chemical reactions. Here you can see that the chemical reactions always involve some sort of bond formation or bond cleavage. This bond is broken, new bond is formed here. And in these processes, always electrons are playing important roles. So if we want to study chemical reactions, the behaviors of electrons have to be described. This is a point. Okay? And this is the equation that electrons obey, which is called Schrödinger equation. And according to this equation, the behavior of electrons can be described by this wave function psi, and the energy of electrons and or molecules itself can be described by the energy E. Okay? And in fact, this looks simple, but it's very difficult to solve this equation. And so we have to introduce many approximations, but here today we don't have time, so let me skip a lot of explanation here. Anyway, let's accept that after introducing a lot of approximations, this very difficult partial differential equation can be converted to this kind of matrix equation, and then we can use the properties of matrices to solve this equation to get energy E. So this energy E is a very important quantity that we want to get. And once we get energy, we can discuss the reaction mechanisms, because we can get reaction barriers for various mechanisms. For example, when the, yes, here I'm comparing two mechanisms. And for this mechanism, the reaction barrier is lower than that for B. That means the mechanism A is more favorable than the mechanism B, and that way we can understand the real mechanism involved in the reaction between reactants and products. Okay, but today's topic was matrices, so let me tell you a little bit more about matrices. The Hückel method is the simplest method of solving Schrödinger equations, and this method was used very actively about 50 years ago. And here is an example for ethylene molecule. This ethylene molecule actually contains 16 electrons in the molecule, but it's not so easy to deal with all the electrons. So instead of dealing with all electrons, we just care about the so-called pi electrons involved in the double bond. Then we can consider only 2 electrons out of 16. And now we will try to get a wave function for these two molecules. And for that, we first assume that the wave function is described like this. And here I don't explain too much, but these phi1 and phi2 are fixed functions. So that what we have to do is to get C1 and C2 coefficients. And to solve this problem, we use a variation principle. I don't want to discuss it. But anyway, at the end of the day, we will get this kind of matrix equation. And all we have to do is transform to matrix equation. So by solving this kind of equation, we get, for example, energy of electrons. Okay? But here, there are many concepts like Hermitian or unitary that you have not learned yet. So let's not discuss any more mathematics. Instead, let me tell you a story about a Japanese professor, Kenichi Fukui, who was the first to get a Nobel Prize in chemistry in Japan. When he was a high school student, he liked mathematics very much. But he was not very sure whether he should really choose mathematics in the university. So he consulted a famous professor, and the professor advised him. And what he said was, if you like mathematics, you should pursue chemistry. Okay? And Professor Fukui actually followed his advice and chose chemistry in the university. And I think that was a very good decision, because later on Professor Fukui proposed a very famous frontier orbital theory. And this theory was developed by doing Hückel calculations that I mentioned. But at that time, there was no good computer. So his students used this kind of mechanical calculator. I don't know how to use it, but you will, yeah, anyway. His students did a lot of Hückel calculations using this kind of calculator. So, what I wanted to say here is that I think this advice applies to you because you like mathematics. And I think you have a chance to make a big discovery in chemistry. And I really encourage you to study chemistry in the future by using the knowledge of mathematics. And, okay, so I think I'm running out of time. So I wanted to tell you a bit more advanced method, but let's not discuss it. Anyway, again, I will get a similar matrix equation and get energy. Yeah, we always this kind of calculations in quantum chemistry. Okay, so it's about time. And okay, so what I wanted to tell you today is that if you learn matrices, you can study a variety of problems in the real world. And as an examples, I showed you chemical and biological molecules, but there must be many other applications in the real world. And in the applications, computers can save our energy a lot. Okay, so there are a lot of benefits if you learn matrices. I hope you enjoy your future studies at MAS. And yes. And finally, I would like to thank Dr. Daniel Moskovich from Mass for taking care of this seminar. And I thank group members for helping me with the presentation. And if you have any more questions, please feel free to visit my office. You can easily find my office because sometimes an empty bottle of energy drink is placed. Thank you very much.
Okay, ladies and gentlemen, thank you. Let's give another round of applause to Professor Hirao for his wonderful speech and presentation. So now I invite the organizer for today's seminar to come down and give a total of appreciation to Professor Hirao.
Hi everybody. All right. Seriously, we thank you, Professor Hirao, for coming today, and very nice having him here. And I hope you guys enjoy this. And okay, give me a second. All right, guys. You guys are very welcome to provide feedback, as we have set up a Facebook page as well. So you can actually like our Facebook page, and if you have any feedback or suggestions, you are welcome to write on our Facebook post, Facebook wall, or you can email us, or you can drop us a PM. Yeah, and we really need your feedback because that's the only way we can improve from time to time, because we don't know whether you enjoy this or not. Well, of course, I hope you enjoy this. We need improvement, yes. So, and please tell your friends about these seminars, and hopefully you think this is helpful. Okay, thank you. Yeah, if you have any questions on finding the Facebook page, you can search SBMS-MAS, then I think you should find the page easily. And we also have a refreshment outside. Yeah, feel free to take a drinks or enjoy the food.